Okay, so I've got the so-called Atwood machine set up here, which amounts to two masses, a pulley, and a string. Very simple. And we've analyzed this in class. So today we're going to look at some energy considerations for the Atwood machine. This would be M1, this is M2, and this is the height between M1, well, the bottom of M2 and M1. So what we would do is, and I'm going to, of course, send you this data, I'm going to let it go. M1 is heavier than M2, and you time it. So 1, 2, 3, go. Okay, we do 3 trials on that, get an average time, and then we'll calculate the acceleration. By knowing the acceleration, we can calculate the final velocity of the masses, and I'll go to the board and we'll talk about some energy considerations. So here's the drawing of the Atwood machine, the pulley, M1 and M2, and this is that initial height that we started with for M1. Very simple to calculate the theoretical acceleration. It's simply M1 minus M2. Remember, M1 is greater than M2, so we're just looking at the magnitude of the acceleration here, and it's divided by the total mass of the system, and you multiply that by g. And just like we've done several times now, the experimental acceleration is 2h over the average time squared. So I will send you the average time and the height for different sets of masses. Like the one that we had on there today was, I think, a 40 and 50 gram, and then we've got a 190, 200, so we'll increase the total mass of the system. So let's think about energy. The final velocity, I hope you would agree that when that mass M1 touches down and hits the ground, both of these objects have the same speed. Okay, so they have the same magnitude of velocity. So for the final velocity of the system, it's simply the experimental acceleration multiplied by the average time. Okay, and you should find that there is going to be a difference, certainly a difference between A experimental and A theoretical, because you've got friction that's unaccounted for. We have the rotation of the pulley. Some of the energy goes into actually rotating the pulley. Air drag, we could talk about some other things as far as uncertainties. So on the left side of the equation, this is the available energy to the system. This is M1GH. That's the potential, that's the initial potential energy of M1. And then the final potential energy is M2GH. And the difference between those two is the change in potential energy. That should equal, just by work kinetic energy, that should equal the final kinetic energy of the system if there were no losses. So the final kinetic energy of the system is 1/2 M1 V final squared plus 1/2 M2 V final squared, plus this term that I'm calling E lost. So that sort of lumps in the things that I just talked about. The losses to friction, the energy that went into the rotation of the pulley, air drag, those kinds of things. So what I want you to calculate, I want you to calculate E lost based on your experimental acceleration and your experimental time. Now, should this value be positive or negative? Well, the way I've written it, you should get a positive value for E lost to make this system balance, because your V finals will be less than they should be if there were no losses. Okay, so you'll calculate E lost.